This chapter studies the economic order quantity problem with quantity discounts. Unlike the classic EOQ setting, unit price is no longer constant. Larger order quantities can unlock lower unit costs, but they also increase average inventory and holding costs. The goal is to choose an order quantity that minimizes total annual cost when discounts exist. Megamart faces a procurement decision with a three-tier discount schedule. Orders below 1,000 units cost $5 each. Orders from 1,000 to 2,499 cost $4.85. Orders of 2,500 or more cost $4.75. Demand is 12,000 units per year, ordering cost is $50 per order, and holding cost is 20% of item value. The decision must balance price savings and inventory investment. Tier 1 builds a mathematical formulation that explicitly chooses a discount tier and an order quantity. Only one tier can be selected, and the order quantity must lie within that tier's quantity range. The objective adds ordering cost, holding cost based on the tier price, and purchasing cost based on annual demand and the tier price. This slide defines the sets and parameters. Discount tiers define unit costs and quantity ranges. Demand and ordering cost determine ordering frequency, and the holding rate converts unit cost into annual holding cost. Decision variables include order quantity and a binary indicator that selects the active tier. The objective function computes total annual cost under each possible tier and uses the tier selection variable to activate exactly one. Holding cost depends on order quantity and unit cost. Ordering cost depends on demand divided by order quantity, and purchasing cost depends on annual demand times unit cost. The constraints enforce that exactly one tier is selected and that the order quantity is feasible for that tier. A big M term allows the quantity bounds to be relaxed for tiers that are not selected. This structure makes the problem a mixed integer program, but in most practical cases there are efficient heuristics that avoid full optimization. This figure visualizes the discount cost structure. As quantity increases, unit cost drops in steps. The key insight is that the best order quantity may sit exactly at a breakpoint, because that is where you qualify for a lower price without ordering too much beyond what is necessary. In practice, a standard approach is to evaluate each tier separately. For each unit cost, compute the EOQ as if that price applied. If the EOQ does not meet the minimum quantity for a tier, adjust up to the tier minimum. Then compute the total annual cost and compare across tiers. This EOQ per tier formula shows how unit price affects the optimal quantity. Lower unit costs reduce holding cost per unit, which tends to increase EOQ. However, discount tiers also impose minimum quantities. That is why the final candidate quantities often include tier breakpoints as adjusted solutions. This two-tier example demonstrates the logic. The Tier 1 EOQ is feasible and produces a total cost of $12,490. The Tier 2 EOQ is below the minimum, so it is adjusted to $1,000. Even with higher holding costs from ordering more, the discount reduces purchasing cost enough to produce a lower total cost of $11,995. Tier 2 focuses on the classic three-step heuristic. It is efficient because it scales linearly with the number of tiers. The algorithm computes EOQ for each tier, adjusts to feasible quantities, and then selects the quantity with the minimum total annual cost. This is often sufficient for real procurement planning. This figure summarizes the three-step heuristic process. The method is systematic and easy to implement. It also produces a transparent explanation for why a larger order is selected. The cost breakdown shows exactly how purchasing savings compensate for increased holding costs. This slide reports the concrete example output. Tier 1 orders about 490 units, while Tier 2 must order 1,000 to qualify. The Tier 2 option has a lower total annual cost, so the selected policy is to order 1,000 units in the discounted tier. Tier 3 addresses complex discount structures and constraints. When there are many tiers, storage limits, or additional business rules, heuristic evaluation may not be enough. The water cycle algorithm is a meta-heuristic that models candidate solutions as raindrops flowing toward better solutions, with evaporation and raining to escape local optima. This flow update rule shows how a candidate solution moves toward a destination such as the sea or a river. Random scaling creates exploration. This mechanism allows a population of solutions to gradually concentrate around good quantities while still maintaining diversity. This figure shows the water cycle algorithm structure in the EOQ setting. The sea represents the best solution found so far, rivers are strong alternatives, and raindrops explore the space. In an inventory context, the algorithm evaluates cost while enforcing constraints like storage capacity, so it can find a feasible quantity that balances discount benefits and inventory limits. In this part, you can see the implementation details in action. The key class visible here is the Water Cycle EOQ Optimizer class. Key functions in this chunk include initializer, objective function, and initialize population. You will notice logic related to demand, population, iteration, objective. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to validate this chunk against a small hand-computed example, so you can trust it before using it in production. In this part, you can see the implementation details in action. Key functions in this chunk include identify water bodies, flow to destination, and evaporation and precipitation. You will notice logic related to fitness, population, iteration. As you read it, follow the data flow from inputs to outputs and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, you can see the implementation details in action. Key functions in this chunk include optimize. You will notice logic related to fitness, population, iteration, objective. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include demonstrate. You will notice logic related to demand, fitness, population, iteration. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, we move from the idea to the mechanics of the implementation. As you read it, track what is computed, what is stored, and what gets updated each iteration. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. This example output shows a constrained case with storage capacity and a 5-tier discount structure. The water cycle algorithm selects an order quantity of about 1,837 units. The selected unit cost is $9.25, and the resulting annual cost is lower than simple tier-by-tier candidates. This demonstrates the value of meta-heuristics under constraints. These practice questions help you apply the approach. First, you formulate and solve the mixed integer model for a discount schedule. Next, you implement the 3-step heuristic for a 4-tier case. Finally, you design a water cycle algorithm variant that includes storage and seasonality constraints and analyze convergence over many iterations. The takeaways are straightforward. Quantity discounts change the EOQ decision because purchasing cost now depends on order quantity. In many cases, tier-by-tier evaluation and the 3-step heuristic are sufficient and transparent. When constraints and tier complexity grow, meta-heuristics provide a flexible way to search for better feasible solutions,